In methods of approximation, so far we have dealt with Hamiltonians that do not depend explicitly on time. But in nature, most quantum mechanical phenomena are governed by time-dependent Hamiltonians. So now, today we are going to start to deal with the concept in which we will consider the approximation methods treating Hamiltonians that will depend explicitly on time. In fact, particularly to study the structure of molecular and atomic systems, we need to know how electromagnetic radiation interacts with these systems. Molecular and atomic spectroscopy, deals in the essence with the absorption and emission of electromagnetic radiation by molecules and atoms. And as a system absorbs or emits radiation, then it undergoes transition from one quantum state to another. During the absorption or emission of energy or radiation, definitely there will be a change in the quantum state of our system. In fact, the aim of the time-dependent perturbation theory is to study such processes of absorption and emission of radiation by atoms, or more generally you can say for treating the transitions of quantum system from one energy level to another. Okay, so basically the time-dependent perturbation theory deals with to find the transition probability of the system when it undergoes one unperturbed eigenstate to another unperturbed eigenstate. Okay. In other words, you can say that if the system is initially in an unperturbed eigenstate, let us say kate psi I, okay, then the Hamiltonian, this kate psi is the unperturbed state of the unperturbed Hamiltonian H naught. Okay. In fact, this time-dependent perturbation theory then aims to find the probability that the system will be found at later time in another unperturbed state, kate psi f. Okay. So this is the aim of the time-dependent perturbation theory, which is the subject matter of our today's lecture. In fact, when you will consult the different textbook to deal with the basic theory of this time-dependent perturbation theory, you will see that different writers, different authors have followed the different techniques or different methods or different approach to discuss this theory. In fact, since here time evolution is present, so the most important, or you can say the most convenient method to discuss the time-dependent perturbation theory is in terms of the interaction picture. In fact, in my previous video on quantum dynamics, I have provided videos on three pictures: Schrodinger picture, okay, the Heisenberg picture, and the interaction picture. So actually, in this calculation, I will prefer to use the procedure to discuss the time-dependent perturbation theory by using the interaction picture. So definitely, if you have not a concrete knowledge of interaction picture or different pictures, definitely you should watch my video on the three pictures which I have already uploaded earlier. Okay. If you have a concrete knowledge of this interaction picture, then you will be able to understand this concept very easily. Okay. So definitely you should watch my video on interaction picture in the playlist of quantum mechanics, which I have already uploaded earlier. Okay. Now, in this first lecture on time-dependent perturbation theory, we will see the basic concept or basic theory of this time-dependent perturbation. We will actually obtain the general expression for the transition probability. It means the probability by which a system transits from one unperturbed state to another, initial state to final state. What will be the probability of that transition? We will actually calculate in this first video on time-dependent perturbation theory. And after this, we will consider two special cases, that is, we will actually calculate the transition probability when the perturbation will be constant and when there will be harmonic perturbation or the periodic perturbation. Okay? But that will be dealt in my forthcoming video. In present video, we are going to see only the basic theory of this time-dependent perturbation theory. You have already learned about the time-independent perturbation theory. So like a time-independent perturbation theory, let us consider there is a system which is described by a Hamiltonian, which can be splitted into two parts. Okay? The first part of the Hamiltonian of the system is H0, and this H0 is time-independent part of the Hamiltonian of our system. Okay? And the another part will be definitely here time-dependent. In case of time-independent perturbation, the another part which is called perturbation, that was also time-independent. But in this case, the perturbation term, which is denoted by the symbol this V of t, this is also time dependent. Okay? And as in case of the time independent perturbation theory, you have seen that this perturbation term is much smaller than this Hamiltonian H0. Okay. So in this case too, we will consider that the time dependent part of the Hamiltonian denoted by the symbol this V of t is small in comparison to this H0. Okay. In fact, here this H0, describes the system when the system is unperturbed. Okay. And it is assumed to have an exact solution that are known. Okay. Such a splitting of Hamiltonian is encountered in typical problem, and so let us consider the system which when is unperturbed, that is described by a time independent Hamiltonian, let us say H0, and whose solutions are the eigen values En and the eigenstate kate psi n. So, if H0 is a time independent Hamiltonian, okay, and the eigenvalue and the eigenfunction of this H0 are exactly known, then the Schrodinger equation for this H0 can be written in this manner: H0 kate psi n equal to En kate psi n. This is actually the energy eigenvalue. Here it is understood, you must understood that this En and kate psi n are known, or you can say that this equation 2 is exactly solvable. And you can see, as I have told you, that in this theory we consider that the Hamiltonian H of our system will be splitted into two parts. First part is H0, which is time independent and it is exactly solvable, and the another part which is smaller with comparison to H0, that is the perturbation term, that is V of t. Okay. In fact, in most of the general case, this state vector is given in this manner. This is ket psi n of t. Here I have written capital psi n. This is the actually the most general state vector of given by this stationary states. Okay, and this ket psi n of t is given as e to the power minus iota times t h naught over h bar times ket psi n. Here ket psi n, this is the eigen state of this unperturbed Hamiltonian h naught. Okay, or you can also write in this manner in terms of the energy eigenvalue. This is equal to e to the power minus I e n t over h bar ket psi n. Okay. Now, in the time interval between 0 and tau, we subject our system to an external time dependent perturbation, let us say V of t. And as I have told you that this V of t, which is actually the perturbation term, this is much smaller than this h naught. And how this V of t varies with time, let us see. In this time interval between 0 and tau, this V of t is actually equal to V of t. It means it varies with time. But before t equal to 0 and after t equal to tau, it is 0. Okay. So you can say that during the time interval 0 to tau, the Hamiltonian of the system, which is actually h naught plus v of t, and the corresponding Schrodinger equation will be what? What will be the corresponding Schrodinger equation for it? This is time dependent Schrodinger equation I h bar d psi by dt equal to h psi t. But instead of h, now we will write h naught plus v of t. Okay. Here you know this v of t actually characterizes the interaction of the system with the external source of perturbation. Okay. How does this v of t affect the system? How this perturbation affects the system? When the system interacts with this v of t, that is the perturbation potential, it either absorbs or emits energy. Actually, this process inevitably causes the system to undergo transition from one unperturbed eigenstate to another. And our main task of time-dependent perturbation theory consists of answering this question. So, if the system is initially in an unperturbed eigenstate, let us say ket psi I, okay, of the Hamiltonian h naught, then what will be the probability that the system will be found at a later time in another unperturbed eigenstate, let us say ket psi f? This answer of this question will be found in this video, and this is actually the aim of the perturbation theory. Okay. In fact, to prepare the ground for answering this question, we need to look for the solution of the Schrodinger equation, which I have written here in this equation 5. We have to solve this. You know, actually the solution of this Schrodinger equation is found by different standard methods. Okay. When you will consult the different standard text, then you will see that in some authors have expanded this psi of t in terms of the expansion coefficient, and then they get the solution of this Schrodinger equation. Okay. But instead of that process, here, as I have told you earlier, we will follow the procedure. We will follow the procedure of the interaction picture, because instead of following the expansion process, since we are dealing with the time dependent potential, so it will be more convenient to solve this equation number 5, that is the Schrodinger equation, in the interaction picture. That will be more convenient. So I have told you in beginning of my lecture that we will actually adopt the technique of interaction picture to discuss the basic theory of time dependent perturbation. Okay. So now in according with the interaction picture, you may write I h bar d psi by dt equal to Vi of t operated on psi t at here I means interaction. Here the subscript I refers for the interaction picture. Okay. Actually, this psi t of I, how it is defined? When you will watch my video on interaction picture, then you will find that this psi t I is defined in this manner. This is e to the power I t times h naught over h bar ket psi t. Okay. And this perturbation term Vi of t, this is defined in this manner. It is e to the power I t h naught over h bar V of t e to the power minus I t, okay, minus I t times h naught over h bar. Okay. So these definitions you will get when you will watch my video on interaction picture. Okay. Actually, the time evolution equation, which is written in this manner, ket psi t equal to this unitary operator u hat t comma ti psi t, may be written in the interaction picture in this manner. You can see psi t I, this is equal to e to the power I t h naught over h bar ket psi t, and this is equal to this much. This is e to the power I t h naught over h bar u of t comma ti ket psi ti, and this can be written as e to the power I t h naught over h bar u hat t comma ti, and for this we will write e to the power minus I h naught ti over h bar ket psi ti I. Okay. This has been written on the basis of the results of interaction picture. Or this result may also be written in this manner. Psi t, ket psi ti is equal to u I hat t comma ti psi t I. Okay. Actually, here the time evolution operator is given in the interaction picture by this result. You can see this is the time evolution operator. This is given by e to the power I t h naught over h bar u hat t comma ti e to the power minus I h naught ti over h bar. Okay. Now we will insert the equation number 8 into equation number 6. You can see this is your equation 6, and we will make use of the equation 8 in that very equation. And when you will use equation 8 into equation 6, you will get I h bar dui t comma ti over dt, that is equal to Vi of t times ui t comma ti. Okay. In fact, the solution of this equation with the initial condition that this initial condition, uit comma ti is equal to a unit operator are given by this integral equation. Uit comma ti, this is equal to 1 minus I over h bar integral from ti to t vi t dash ui t dash comma ti dt dash. Here instead of writing t dash, you may write t. But since here I have written t as upper limit, so this variable has been changed. This does not make any difference. You are free to write t instead of t dash. But mathematically it is more suitable to write this t dash. Okay. In fact, this time-dependent perturbation theory provides approximate solution to this integral equation. Okay, and if your aim is to find the first order approximation, that can be obtained by taking ui t dash comma ti is equal to a unit operator. Okay, and when you will insert this in this integral sign, then your result will be ui1 t comma ti equal to 1 minus I over h bar integral of vi of t dash dt dash, okay, ti to t. Okay. Now, actually, this result which you have actually obtained here, in this condition, if you substitute ui t dash comma ti equal to ui 1 t dash comma ti in the integral sign of this equation 11, okay, then you will get the second order perturbation. And what will be that result? That will be ui2 t comma ti. This is second order perturbation. And this will be 1 minus I over h bar integral from ti to t vi of t dash dt dash plus minus I over h bar square ti to integral ti to t vi t1 dt1 times integral ti to t1 vi t2 dt2. Okay. So actually this is called the iterative method. Okay. So when the perturbation term vi of t is small, then proceeding by this iterative process, you can get any order perturbation. Okay. So in this same manner, you can obtain the third order approximation. Okay. And for that you have to substitute this into that very equation. So if you will repeat this iterative process, then in general you will get this result. Uit comma ti is equal to 1 minus I over h bar integral ti to t vi t dash dt dash plus minus I over h bar square integral ti to t vi t1 dt1 times ti to t1 vi of t2 dt2 plus so on plus nth term, this is minus I over h bar whole to the power n integral of vi of t1 dt1 from ti to t vi of t2 dt2 ti to t1 times vi t of t3 dt3 ti to t2 and so on, and finally ti integral ti to tn minus 1 vi tn dtn and plus so on. Okay. Actually this series which we have obtained in this equation 13 is known as Dyson series. This is called Dyson series. Okay. And this series actually allows for the calculation of state vectors up to the desired order in perturbation. Okay? But we are now equipped to calculate the transition probability. It may be obtained by taking the matrix element of this equation 13 between the eigenstates of the Hamiltonian H0. Actually, time-dependent perturbation theory, where one assumes knowledge of the solution of the unperturbed eigenvalue problem, which I have defined in this manner, H0 operated on ket psi n is equal to En ket psi n. Okay? So the ultimate aim of time-dependent perturbation theory is to find the solution of this unperturbed eigenvalue problem. Okay? And this actually deals in the essence with the calculation of the transitions probabilities between the unperturbed eigenstate ket psi n of the system. Okay? So now we will talk about the calculation of the transition probability. Okay? So this is the actual ultimate aim of this perturbation theory, time-dependent perturbation theory, you know. In fact, the transition probability corresponding to a transition from an initial unperturbed state, let us say ket psi I, to another unperturbed state ket psi f, can be obtained from this result which we have obtained in equation 13. Okay? This can be obtained. And this is the probability of transition from the initial unperturbed state ket psi I to the final unperturbed state ket psi f. If you denote this probability by the symbol PIF of t, then this is defined as a square of the modulus of the expectation value of this ui of t comma t1. Okay? And this, on the basis of equation 13, you can write this expression. But here, while writing this expression, we have used these results. The expectation value of Vi of t dashed between the states psi I and psi f. This is equal to brass psi f e to the power h naught t dashed over h bar v t dashed e to the power minus I h naught t dashed over h bar ket psi f. And this is equal to this quantity times e to the power I omega fi t dashed. Actually, what is this omega fi? This is actually the transition frequency between the initial and the final levels I and f. And how it is defined? Omega fi is defined in this manner. This is ef minus ei over h bar. Okay, you know. Ei is the energy for the initial state of the system and ef is energy corresponding to its final state. And this is equal to 1 over h bar. Now you know what will be the value of ef? Ef is the expectation value of h naught for the state psi f, and ei is the expectation value of the Hamiltonian h naught for the state psi I. So instead of ef, you may write this much, and instead of ei, you can write this much. Okay? So in this way, omega fi is defined. So when we will use these results, then the transition probability PIF of t on the basis of the Dyson series is obtained in this manner. This is a square of the modulus of psi f uit psi I, and that will be equal to a square of the modulus of a scalar product of psi f and psi I minus I over h bar integral 0 to t e to the power I omega fi t dash, okay, and then psi f v psi I dt dash plus, I am not telling repeatedly bra and kit, okay, and this plus minus I over h bar whole square summation over n integral 0 to t e to the power I omega fn t1, okay, psi f v t1 psi n dt1 times integral 0 to t1 e to the power I omega ni psi n v t2 psi I dt2 and plus so on, okay. So this is the general result for the transition probability. But in most of the problem, we will be interested only in the first order transition probability, only in the first order, okay. Because you will see later on, the higher order transition probability is not very significant in most of the problems of atomic and nuclear physics. The first order transition probability gives the accurate result, okay. So for the first order transition probability, for which this state kate psi A is transit to the state kate psi f, but I is not equal to f, and then actually if psi I and psi f are different, then this term, this scalar product will be equal to 0, because you know this eigenfunction is orthogonal, and if these two functions are different from one another, then since they are orthogonal wave function, so this product will be 0. And if this product is 0, then what will be actually the first order transition probability? If your aim is to find the first order transition probability, you will terminate this series at the first order term, okay. You can see this is your first order term, okay, first order. This is your second order term, okay, and in this way we will write the third order, fifth order and nth order term. But since we are now talking about this transition probability only for the first order perturbation, in that condition this PIF of t will be simply equal to this much mod square. But since I is different from f, so this product will be 0, and therefore Pi of t will be simply equal to a square of the modulus of this second term. I think we have clearly understand. So the first order transition probability, this will be given by this expression, okay. This will be given by this expression, you can see, okay. There was a sorry, and therefore PIF of t is given by this expression, as I have told you, okay. In fact, in principle we can use this equation which I have mentioned here, equation number 14, to calculate the transition probability to any order in this perturbation Vi of t. However, terms higher than the first order become rapidly intractable, okay, and therefore for most problems of atomic and nuclear physics, the first order, that is the result which we have actually defined in this equation A, gives the sufficiently correct result, and therefore we do not try to find the second order transition probability, third order transition probability, because there is no need in most of the quantum mechanical problem, okay, particularly in atomic and nuclear physics. Okay. So now actually, as I have told you earlier, that in our forthcoming lecture, we will see to calculate this transition probability particularly for two cases. Okay. And that will be actually the case of constant perturbation and the harmonic perturbation, or you can say the periodic perturbation. Okay. So in this lecture, I have obtained only a general result for the transition probability. But what will be this transition probability when the perturbation is constant, when the perturbation is harmonic? This is the subject matter of our forthcoming video. Okay. So I think you have clearly understand the basic theory of this time dependent perturbation, and as I have told you, for understanding this calculation, you must have a concrete knowledge of interaction picture. So if you lack in it, then you must watch my video on the 3 pictures which I have provided earlier in my playlist Quantum Mechanics. Okay, thank you very much.